All right, yeah, we can, and we can go. I know I know there are a couple people going to come by, but they've heard me before on this. So I don't think.
All right, so thank you all for coming out. Our next speaker is Jim Barafaldi from TRC. He's going to be presenting EPA other test method 37 is an improved way to measure particulate matter emissions from low emitting sources. Jim is a senior project manager for TRC, has over 30 years experience in air measurements. He received a bachelor's degree in physics from the University of Texas at Austin. Over his career, Jim has led projects for many different facilities over a broad range of industries. He is currently focused on the refinery air emissions and industrial flare testing. With that, I turn it over to Jim. And,
thank you, David.
Thank you for coming out.
All right, thank you. I have a couple other people that were going to stop in, but maybe they won't make it. So since there's only a few of us, what is your background in emissions testing with particulate matter? Do you have any knowledge of the subject, or sort of tailor this to what you've had? Okay, so we'll start at the beginning. Good. Well, I've got quite a bit of that. So yeah, it just depends. If I have a bunch of people that have done the methods a bunch of times, then it's a little different presentation. So this is going to be a presentation on other test method 37, which was published by EPA in 2018. It's a revision to some previous test methods that were out for many years before, and some that were out since about 2005 or so. So I'm going to break this up into 4 parts. First, we're going to talk about particulate matter in general. What is particulate matter? How do we define particulate matter? Because we can't really figure out how we're going to test for what we're going to test for if we can't figure out how to define it. Then we're going to discuss measuring for the condensable particulate matter, which is our biggest concern with this method. Then we'll go over the method, and then I'll present some results from a large test program that we did using the method when it was first published. So particulate matter. So most people, when they think of particulate matter, they think of dust or smoke or particles that are coming out of some kind of source that you can see or you can pick up on a filter. And that's your sort of standard particulate matter thought. But particulate matter is actually more complicated than that. Particulate matter can be looked at as 2 main sources of particulate matter that industry experiences. We have primary particulate matter, and that is particulate matter that's actually emitted from a source, directly from the source. So it could be a smokestack, it could be a process vent, it could be an automobile. And then you have secondary particulate matter. Secondary particulate matter is an atmospheric reaction to something that was emitted from the source that later on would become a particulate. And that is typically something that would be ambient air. People would be interested about in fence line monitoring, could be interested in that. But for source testing that I'm going to talk about today, we're not interested in the secondary PM. We're interested in only the primary PM that can be actually attributed to a specific source, because that's the source that's permitted. That's the source that we have to get an accurate number on. The secondary PM is important to the facility, but it's not necessarily important to the source, because typically on a fence line, you can't necessarily tie it down to that one source that's causing your emissions. So when we look at primary particulate matter, there's 2 categories of primary particulate matter. There's filterable particulate matter, and that is what you sort of typically think of as a dust or a soot or actual particles that we can collect on a filter. Like your air conditioning system or whatever standard filter material you would want to use. The next category is condensable particulate matter. And condensable particulate matter are vapors that are coming out of the source that pass through a filter. So the filter can't collect them, but yet they do form a particle very close to emissions to the atmosphere. So right around the stack where that stack gas comes and it's now mixing with ambient air, it then will form a particulate. Those particulates we do want to attribute to the source, as opposed to a secondary particulate, which would be created far downstream, and you wouldn't pick that up right around the source. EPA and industry has typically defined the area where we're concerned with as being between 65 and 85 degrees Fahrenheit. And so that sort of area, when you have your hot stack gas or your vent gas or a process gas that's being released, when it cools to that 65 to 85 degrees, it's considered it's in the atmosphere. We're concerned with the particulate for condensables that are right at that point, not something that's you know, a mile away or after it's had time to react with rainwater or anything like that. So the two categories of particulate matter that most often you see referred to are PM 2.5 and PM 10. It was always PM 10 originally, and then more recently it's been moved really to a PM 2.5 limit. 2.5 is particles that are less than 2.5 microns. And what's important about that is those are the ones that can do a lot of damage when they get very far down into the lungs, and they can also actually into the bloodstream. The larger PM10 particles may cause people with asthma to have trouble and things like that, but they're typically something the lungs can handle. They really can't handle the 2.5 very well. So most of the newer regulations are all geared around the PM 2.5. All of the condensable particulate matter that we're going to talk about today with this method is PM 2.5, because these are vapors that are coming out and they're forming very, very small particles after they come out and they form a particle. So once again, what we're trying to measure is we're looking at the particulate that's right by the smokestack, or actually in the smokestack in the sense of the filterable particulate, not the stuff that's further down away after it's been reacted. So now we want to talk about how does this particulate matter forming. So condensable particulate matter forms because there's some reaction between some of the chemicals that are in the exhaust of the stack and the atmosphere. And so the common precursors that form the condensable particulate matter are acids. So you've got nitric acid, sulfuric acid, hydrochloric acid, and semi-volatile VOC compounds. So those compounds form a particulate very quickly once they enter the atmosphere. The secondary PM that, once again, we're not considered to attribute to the source, it has different precursors. It has like SOx and NOx, VOCs, and ammonia. And those precursors are what would be formed particulate sort of down the road. So the issue with the test methods that we're going to discuss is how do we make sure that we are collecting all of the condensable particulate matter that we're supposed to be from those precursors like the acids and the ammonia and the semi-volatile VOCs, as opposed to the other ones that are from the SOx and NOx and the VOCs, the regular VOCs. Ammonia sort of plays a part in both of them. So once again, what are we trying to measure? Our big question is, how do we define the boundary of that area that we want to measure? In a perfect world, we could put a big collection over the whole refinery or stack, and we could collect all of that particulate matter, but that's not going to happen. So we have to come up with a method that's going to allow us to sample in-stack gas and simulate what happens when that gas gets exposed to the atmosphere and forms the particulate matter, so we can accurately measure that. Without measuring the secondary PM, we don't want to form that in the stack because that's not going to apply to what we're looking at. So traditionally, this is a standard method 5 sample train. Method 5 was developed to measure filterable particulate matter. So this is sort of the beginning of your stack testing for particulate matter. And so it incorporates a heated probe that comes into a heated filter. So filter particulate matter collect on the filter. Following that, the gas is condensed in a water bath, and this will use to determine moisture of the stack gas, but not in the particulate. So with EPA method 5, we're looking at filterable, which is what we consider front half particulate matter, just this section right here. This gets rinsed, this gets collected, it all gets gravimetrically weighed. We determine how much particulate we pulled out of the stack. So that would be our regular filterable particulate matter. The current EPA method 202 is the back half of the method 5. So it incorporates a method 5, and following that, it incorporates a different set of glassware that's designed to collect particulate matter. And this method was designed to try to simulate what the atmosphere is, but there are some limitations, and so we're going to get to that here in a minute. So what front is the same as what we just saw. Heated probe, heated filter hole, reflects the particulate on the filter. Following that, any of the vapors coming through here get condensed in a non-contact condenser and collected in glassware. Glassware, because it's collecting this, it's all maintained at a 65 to 85 degrees again, to try to simulate the atmosphere. And following that, it gets collected. Any of the particles get formed in this section get collected on this filter. And once again, this is gravimetrically weighed on this section to determine your particulate matter for density. The downside of this and the older method, they revised to several times over the year. The current method is this one. Previously, they actually had this these liquids going through an ice bath. Well, the problem with that is we were going way below 65 degrees. So we were freezing the stuff basically and knocking out a lot of compounds that normally wouldn't be collected in the stream. And we were biasing the particulate matter hot. So the newer method that's presented here has this section here that's maintained at 65 to 85 degrees. However, it's got some issues because as the liquid condenses in here, like if you have a high moisture source, something like 15% moisture, in this condenser be dripping into this container, and this container is going to fill with water. Well, the gas is still sort of contacting that water. It still has a possibility to be dissolved in that condensate water that could lead to some interferences. So the advantages of 5202 is stack testing is very familiar with the method. Pretty much any stack testing company out there does this on a regular basis, and there's not going to be any issue in finding finding people that are competent to do this method. The disadvantage is because what I mentioned with the water content, it can overestimate the CPM, especially when you're looking at very low levels on a very low source. So some of the sources now have permitted level limits that are very, very low, and any small error in the CPM measurement with a 5202 or any of the precursor bias we're talking about with some formation of compounds you're not interested in, they may bias it enough that you're over your limits. So the detection limit of the 5202 has always been a difficult thing to define, and to increase your definition, increase your detection limit. Typically, the answer is to run a longer test run. You pull more gas through the train, you run for 4 hours instead of 2 hours, you run for 6 hours at sometimes. Then you run into other issues because now you have a lot longer time that those compounds are in contact with the liquid that's in the sample train, and you can have even more issues. So OTM 37, which is the method I'm going to finish talking about today, it is a new approach to CPM measurements. So this method is built upon a CTM 39, which was published in 2004, and it is a dilution method of sampling particulate matter. So the idea there is that we want to take ambient air and we want to dilute the sample so we do not have any condensed moisture in the train. So now we no longer have any moisture in the train at all. We don't have any possibility of those compounds being dissolved in that moisture and forming any artifacts. So the OTM 37 training, front part of this, the probe, and this is a PM 2.5, PM 10 nozzle that actually breaks the filterable particulate matter into PM 10 to 2.5 sections. That didn't show on the other train, but yeah. We have a heated probe. This bring the heated sample in. We then blow in clean, dry, ambient air, and it mixes with the heated sample in a special mixing chamber. And then in this chamber here, this is maintained at your 65 to 85 degrees. It's an imitation of the atmosphere. No liquid here. There's no way for any of the vapors that are here to condense. We maintain the temperature and the dilution ratio to verify test runs, make sure we verify that it's not going to condense in here. And then following the this reaction chamber here, a slipstream of that sample is pulled out and measured on a 47 millimeter ambient style filter. And so we've measured the filters on the inlet where we've taken the dry air in. So we have an ultra filter, we have cool dry air ultra filter. It then samples how much our background is, which typically we found to be very, very low. And that clean air comes in, mixes in here, then we sample here, and this filter right here will then give us how much particulate matter we generated in this chamber through the condensers. We estimate that the improved sensitivity of this, the dilution, you're going to lose some sample because you're diluting at 20 to 1 or 10 to 1. In most cases, we ran 20. Sensitivity, you're diluting it by 20 to 1. However, because of the sample media we're using with these filters, we're using ambient level filters that can weigh down to the nanogram, whereas the typical method 5 filters are only weighed to the at best about a half a milligram, so about 500 micrograms, about the best they can do, and these will go down to a few nanograms. So we estimate that the net of the method gives a whole gain in sensitivity. So our low detection limits that we've experienced have reflected that. So we get a much more sensitive measurement of what we have there. There's not as large of a blank that you have to worry about, where you have a lot of reagents and the precursors that are in the water. So let's see, so the sample train, this is what it actually looks like in person. So this is the heat filter box. This is the probe sort of behind this console. This is the chamber that I was talking about. The ambient air that's entering into the mixing cone is right here in front of the chamber. And right here coming off the bottom is the filter that's then on the sample. There's an additional right here on top that will measure the ambient, how clean our ambient air is. The system is all computer controlled. The console here controls the flow rates. There's a large blower that's connected to this line here that's blowing in the clean ambient air. Second blower on this line here that's connected to the back that's pulling the exhaust air out of the system. So by balancing the ambient air in and the exhaust air in, they then determine how much flow is coming in back. So it's computer controlled. That once we get it, set it up, there's not much the operator does except monitor the these computer screens to make sure that everything is within spec. Here's how it looks like on our test program that we were doing it in the field. We did quite a bit of it out of cranes. We didn't have sample stack, some platforms on some of these. This is the console and the mass flow controllers that control the flows of the filters. Set up there. Here's the actual probe and hot box hanging on the monorail that's in the that's off screen to the left. Apparatus where we pull and dry the incoming air. There before that cool air goes in. So now we'll get to sort of what we have experienced on this. We were involved in this method early on, and in 2018 it was published. It went, the final published Federal Registry was like in July or so 2018. Well, we started a large testing program in a refinery in the beginning of 2018. So while the method was in final publication and after it was published, we conducted a testing program on 50 boilers and process heaters. They ranged in size from small ones that are only like 10 million BTUs up to 1,100 million BTUs an hour. Most of them had refinery fuel gas. A few of them had some other off gases, but for the most part, it was refinery fuel gas. Relatively low sulfur content of 60 to 110. And some of them had very low limits. And we had tested many of these units before using 201A and method 5 or 202 or 201A and 202. And we had gotten acceptable results in the past, but there were always more variability in the results than what they cared for. And in the interest of trying to get more accurate numbers, they decided to try out this method. We ran short test runs. They were only like 2 to 2.5 hour long test runs, as opposed to running extended test runs. What we found on our results after this program was that the new method, the OTM 37 results, were consistently below the AP42 factors by a considerable amount. The orange dots on this chart are historic EPA 201A 202 or method 5 202 results for the same units at this location. So you can see some of them vary quite a bit all over the place. All the units on the orange dots were tested on the blue triangles down below. We don't have a one-to-one correlation here because the customer doesn't want to necessarily publish those data exactly, but they were all retested. We tested a lot more sources actually on the blue triangles than what we had tested previously. We tested some sources that hadn't been tested in many years. And so we found a very consistent results for the OTM 37 that not only gave us the lower numbers, but they were very consistent. We would have 3 test runs that gave us basically the same results. Whereas on the orange dot, sometimes we'd have 2 test runs that gave similar results and a 3rd test run that was really high. And it was hard to describe, why do you have this high test run? Was there something different with the unit, or was there something different in the process? But the OTM 37 gave us very, very consistent results. The other thing that's part of the OTM 37 is they provide in the method a way to calculate the MDL on an ongoing basis of blanks. And some of this that's the method detection limit. And so some of the current PM methods with 5 and 202, they're looking at ways to incorporate this in the new publication of those methods, which should be coming out in the next year or so. But what we did on this program is we're required to collect 7 blanks of our whole train. So we do a whole rinse of the sampling system and we recover that, and that's a blank. And we had to do that at least 7 times before we could get started. And then ongoing, every time we do a new source, we do another one of those blanks. And we take the latest 7 of those blanks and we calculate our MDL. So that sort of is a test on how well is the tester getting consistent data over the time of the test. So we started out, we were still doing pretty well, but if you see the gray line, our method detection limit dropped considerably as we got better and better at the method. And this type of thing is going to be incorporated, I think, into the regular particulate matter testing for all the testers to get an idea on how well they're following the best practices. Because you could tell if someone got really sloppy, that number would really go up. So we were very happy that we were able to get our method detection limit. Actually, this shows we said down to 1,500 micrograms. The lowest we got during the testing was down to about 1,000 micrograms or 1 milligram is about where we got our detection limit at the best point in this testing. And it would go up and down a little bit depending on what those blanks came out as, but very, very successful with the blanks. So overall, the advantages and disadvantages of this method. The advantages are there's no change in the filterable particulate matter measurement and the cut on the PM10 and PM2.5. That is very familiar equipment. It's the same thing that's used on the other methods. We better replicate the formation of the PM in the stack than the 202 because there's no water condensed in the system at all. So we don't have to worry about that. The samples are all collected at like ambient temperature and ambient conditions. So there's no condensation on the filters either. Sometimes in a method 5 type test, at a really high moisture source, you could get the filter. Once it gets out of that hot chamber, you could get a little condensation on that filter. We don't have that with this method. There's no gas liquid contact that we talked about. And then the other thing is the test run length is really important. Sometimes on gas powered like turbines and power plants, we'd run 7 or 8 hour test runs sometimes for clients that wanted to try to get a really low detection limit. With this method, those long test runs are not required. We could run a 2 to 2.5 hour test run to get the same sensitivity that we used to get with like a 6 or 7 hour test run. The other advantage is, I touched on a little bit, is the filters that we're using are ambient filters that are commonly used in ambient air sampling. So there's the laboratories that analyze these filters, they're cartridge filters, they're robotically weighed on a 6-place balance down to the nanogram, and they have a lot of QA in place on these filters and the integrity of the filters and the weighing process. And we're borrowing that ambient technology for this source testing method. And that's where we get an increase in sensitivity and increase in accuracy on the filter measurements. The disadvantages is because this is a conditional test method, it was an other test method, it is not approved for use on all sources as it stands from the EPA. It has to be approved on a case-by-case basis with the regulators. So if you have a low emission source and you're interested in trying to test this out, you can go to the state regulators or the EPA and say, hey, we'd like to use this on the source, and they'll give you your feedback. We use this extensive in several different states, and we haven't had a problem. Other states, aren't familiar with it. They're confused by it. So what some of our clients have gone to do is they've decided to do both. They've gone out and said, well, we're going to spend the extra money and we're going to do a 5202 or a 201A 202, and we're going to do this method at the same time, and then present those results together to the state, and then use that as a justification for what we're doing. It's obviously not the best method for every test out there. Some high emitting sources, you can get very accurate numbers with 5202. The question is on the really low emission sources where there's basically nothing there, you don't want to create things that aren't there. The other issue we ran into is it's a little more of a fair weather method. Because you have to maintain that chamber at 65 to 85 degrees, it's a rather large piece of metal. If it's a really, really hot day, you have to really cool that incoming air. The inlet air needs to be refrigerated. And we ended up actually running it through a bunch of intercoolers, and we actually run a portable air conditioner at one point to get that air as cool as possible. We found if we could get it down to around 70 degrees, then it was sufficient to cool the stat gas maybe at 500 degrees. It was sufficient to dilute that stat gas and keep it in the 85 to 65 degree range. On a really hot day, that can be difficult. A lot of ice is required to try to keep it at that. The other thing is on a really, really cold day, we had to heat it up. Heating things are easier though. So we have a lot of heating blankets and we can easily heat that chamber and maintain it at 80 degrees without much of a trouble. But it is another concern. It's more expensive than 5202. Mainly the equipment is a little bit more expensive. It's more cumbersome, but we also require usually an extra operator. To do the 5202, many test teams can get by with doing that with like 2 to 3 people. On this method, you need 3 to 4 people at minimum. The recovery of the train and assembly of the train, we typically have a person dedicated to that on the job site. Whereas with 5202, that would be a shared responsibility that someone would do that during a test, between test runs, and then during the test run, they would have another duty and they'd be able to do something else. So this does take a little bit more manpower. It's more equipment, it's larger equipment. There's a little more electrical power needed. And then the biggest thing is you really have to have someone that's got some experience in it because of those method detection limits. If someone were to obtain the equipment and just test it out in their backyard, they could get that experience. They could use it for a month or two and get that experience. But it's the type of thing where you have to be very familiar with the equipment, assembling it all. There's a lot to assemble. There's a lot of connections, and having it be a smooth test program, getting our crew up to speed on it was really important. It worked really well. And the further we got into the test program, the smoother it went, and everybody really, we got a lot of people that became real experts at it. But there's a little steeper learning curve than the typical stack testing. In summary, the measurement of CPM is a challenging and evolving field. We have this particulate matter limits that a lot of facilities are dropping and dropping and dropping. And we haven't come up with new methods in a while to try to address how do we measure that. And so this is the latest attempt to measure that. I'm sure the method will be continually evolved over the years. I know they continually improve method 202. That's what's the industry standard right now. But this is, I think, the best option besides 202 for the low emitting sources. The method performance that we've seen has been very stable and very, very good. And then sort of skipping to the very bottom is, will the agency approve it? And that's the big question. A bad argument for approving a method is it gives me low results. That's not our point. We don't want to say this method wasn't designed to give you low results. It's trying to give you more accurate results. And what we found is it gives us much more consistent results, and the accuracy appears to give us much more accurate results. But that doing them paired between 201A and 202 will often get similar results. This method is typically lower results to it. But it's also standard deviation between the results on this method we've seen is much better than the standard deviation on the 201A, 202, which gives us a better precision, which leads us to believe that we're getting a better accurate result. So that's pretty much it. Any questions, or go back over any of the we've been doing about, probably since 2018, we've been doing about 3 or 4 a year for different clients. So we've got 3 sets of the equipment. So we have enough to do, 3 sources at once. And we've used it, I think we did it 5 times in 2021. We've got, I think, 2 scheduled for 2022. So it's not being used nearly as much as 5202 because we haven't had the need on the sources. The ones that we've used it on most are ones that have an issue where their current particulate matter limit, they don't know if they're going to pass. So every time they go and test for particulate matter, it's a cross your fingers and pray we pass. Some sources don't have that problem at all. Some sources have a limit that's significantly higher than what they've ever seen. And because the sources keep getting cleaner and cleaner over the years, and sometimes they don't lower the limits. But in many cases, they say, oh, well, that source has been reading 0.2 pounds an hour for the last couple tests. Let's take our limit from 1 and put it down at 0.25. That source could be something that would be, this could be something they want to look at, because what happens when they have a test that's runs a little higher? But we've had a variety of industries. The large project I described in this was done at a large refinery. However, we've done them at carbon black plants. We've done them at a couple of industrial boilers at chemical plants. There's been some power plant work where they've done it on large frame turbines, things like that. A lot of those that require the long test runs, they've used it on that. and also ones that you don't expect there to be any real CPM. The condensable particulate matter on some sources, for instance, a gas-fired power plant has very low sulfur. Lots of times they're running on, very low sulfur limits from pipeline grade natural gas. Where are they getting the CPM when they do 202? And this method will help, eliminate some of those precursors that they were getting because of the long test runs that they were required to do. They could have some interference, or they could have some method problems during those long test runs. So I see some advantages of that. All right, so I guess that's it. You're welcome.